Imagine holding a piece of a cloud in your hand. Not a photograph of one. Not a simulation. An actual, physical, solid object sitting in your palm, yet so light that your skin can barely feel the weight. This is aerogel. A material so impossibly light it can rest on a soap bubble without popping it. So translucent it looks like a piece of trapped smoke. And so thermally insulating that a blowtorch on one side cannot warm your hand on the other. Scientists call it frozen smoke. Others call it solid air. A few have been known to call it simply impossible. It holds more than 15 Guinness World Records. NASA has used it to catch actual particles that drifted between the stars. And right now, it is sitting between the battery cells of electric vehicles on highways across America, preventing catastrophic fires. So what exactly is this substance? How did it emerge from a bar bet in 1931? And why is this ghostly, fragile-looking material suddenly one of the fastest-growing advanced material markets on the planet? Welcome to Cipher Sci. Let us find out. Our story begins in 1931, in a modest chemistry laboratory at the College of the Pacific in California. A chemist named Samuel Kistler had made a bet with a colleague named Charles Learned. The question between them sounds almost childlike in its simplicity: can you take a jar of jelly, and replace all the liquid inside it with air, without making the whole thing collapse? Learned said no. Kistler said yes. That argument launched one of the most extraordinary materials in modern science. Here is the problem Kistler had to solve. A gel is a three-dimensional lattice of solid particles held in place by liquid, like a tiny molecular sponge. If you simply evaporate the liquid, you get catastrophe. Surface tension, the same force that pulls a wet paper towel flat as it dries, yanks on the lattice walls from every direction, and the whole structure collapses inward. It just crumbles. Kistler's insight was to take the gel above what chemists call the supercritical point, a specific combination of temperature and pressure where something remarkable happens: the boundary between liquid and gas simply disappears. The liquid becomes a supercritical fluid, and it can be coaxed out of the gel without ever generating surface tension. It leaves quietly, without touching the walls on its way out. What remains is a skeleton of interconnected nanoparticles. 3% solid. 97% air. But still, somehow, structurally intact. He called it an aerogel. Aero, from the Greek for air. Gel, because that is what it used to be. Under an electron microscope, aerogel looks like a three-dimensional spiderweb built by a spider the size of an atom. Silica strands just 2 to 5 nanometers wide, that is roughly 20 times smaller than the coronavirus, woven into an interconnected scaffold that is simultaneously almost nothing, and surprisingly strong. The numbers border on absurdity. The lightest aerogels weigh just 1 kilogram per cubic meter. Air weighs 1.2 kilograms per cubic meter. The lightest aerogels are literally less dense than air, physically possible only because the pores trap and hold the air inside. And yet, this near-nothing structure can support up to 4,000 times its own weight. A tennis court-sized panel of aerogel thick enough to stand on could, theoretically, support the weight of a mid-size car. But for most of aerogel's commercial history, its most valuable property is not its legendary lightness. It is what happens when heat tries to get through it. Heat moves through materials in 3 ways: conduction, convection, and radiation. Aerogel defeats all 3, almost simultaneously, and that is what makes it genuinely unique in the universe of known materials. Conduction first. In normal solids, heat is conducted through the material's atomic structure, vibrations passing from atom to atom like a chain reaction. In aerogel, that chain has almost nowhere to go. The solid framework represents only 3% of the total volume, and silica, the most common aerogel-based material, is itself a poor thermal conductor. Heat that enters the material almost immediately reaches a dead end. Convection second. Normally, air inside an insulating material can circulate, warm air rises, cool air falls, carrying heat with it. In aerogel, the pores are smaller than 100 nanometers. That is below the mean free path of air molecules, the average distance they travel between collisions. At this scale, air molecules cannot circulate. They are trapped. Convection is effectively zero. Radiation third. Infrared radiation, heat energy in the form of light, would normally pass right through a transparent material. But by adding small amounts of carbon or other infrared opaque particles to aerogel during manufacturing, that pathway is also blocked. The result is a thermal conductivity of approximately 0.015 watts per meter Kelvin. Standard fiberglass insulation is about 0.04. Styrofoam is similar. Steel is 50. In practical terms, 1 centimeter of aerogel insulates as well as roughly 10 centimeters of conventional foam. That is not a marginal improvement. That is a different category of material. And then there is the color, or rather, the absence of color, the strange blue haze. That is Rayleigh scattering, the same physics that makes the Earth's sky blue. When light strikes aerogel's 2 to 5 nanometer particles, wavelengths at the blue end of the spectrum scatter in all directions. It is not paint. It is not dye. Aerogel literally contains a piece of the sky. NASA engineers discovered aerogel in the 1990s, and they immediately recognized what they were looking at. Space is a thermal nightmare for electronics. On Mars, temperatures plunge to -130 degrees Fahrenheit at night and can climb to 70 degrees above zero in the afternoon, every single day. No insulation designed for Earth could handle that swing in a package light enough to fly to another planet. Aerogel could. Every Mars rover from Sojourner, to Spirit and Opportunity, to Curiosity has relied on aerogel insulation to protect its sensitive electronics through the Martian night. Without it, those rovers would have frozen solid on their first day on the red planet. But NASA's most creative use of aerogel came with a mission to touch a comet. In 1999, NASA launched Stardust, a spacecraft with an audacious mission. It would intercept Comet Wild 2, pass through its dust cloud, and return solid samples to Earth. The challenge: cometary particles travel at up to 13,000 miles per hour. Any rigid collector would shatter them on impact. You would end up with dust. The solution was aerogel. Engineers fitted Stardust with a collector the shape of a tennis racket, covered in aerogel tiles. When cometary particles struck at hypersonic velocity, the aerogel decelerated them gradually, over a distance of a few centimeters, slowing them gently the way a thick foam pad slows a falling egg. Each particle carved a visible, carrot-shaped track pointing back to where it stopped. When Stardust returned to Earth in 2006, it carried over 1 million individual particles trapped in its aerogel tiles, including interstellar dust grains that had been traveling through the galaxy for billions of years before aerogel stopped them in their tracks. Aerogel did not just insulate a spacecraft. It caught Stardust. And in 2025, researchers at Zhejiang University in China pushed aerogel into territory that most materials scientists had considered unreachable. They developed a graphene-ceramic hybrid aerogel that remains fully elastic, bouncing back after being compressed 99%, at temperatures exceeding 2000 degrees Celsius. That is hotter than the surface of most stars. This material is now being considered for deployment on deep space probes, hypersonic aircraft, and even in nuclear fusion reactors, environments so extreme that until now, no practical insulation material could survive them. The science of aerogel is not slowing down. It is accelerating. For decades after NASA's first adoption, aerogel remained largely confined to high-budget, high-performance applications. The material was too expensive. Too fragile. Too exotic for ordinary buildings. That equation is changing. The fundamental value proposition in construction is this: insulation means thick walls, and thick walls mean lost floor space. In dense urban real estate, every centimeter of wall thickness is money. Aerogel changes the math. An aerogel blanket 1 cm thick outperforms 10 cm of conventional foam insulation. You get the same thermal performance in 1/10 the space. Nowhere is this more transformative than in the retrofit of historic buildings. Across Europe, where some cities are mandating 60 to 80% reductions in building heat loss under new net zero regulations, renovating a 19th century stone facade is a genuine dilemma. You cannot add insulation to the outside without destroying the historic architecture. You cannot add it to the inside without shrinking rooms that are already small. Aerogel makes both problems disappear. A thin aerogel layer applied to interior walls provides the required insulation without meaningfully changing room dimensions. Industrial applications have also expanded dramatically. Aerogel blankets now insulate subsea oil transmission pipelines, liquefied natural gas storage facilities, and high-temperature industrial reactors, environments where conventional insulation would degrade or simply could not fit. But the application that truly propelled aerogel from niche technology to major industry is one most people have never thought about: the inside of an electric vehicle battery pack. Every EV battery faces a terrifying failure scenario called thermal runaway. One battery cell begins overheating, from a defect, a collision, or extreme charging stress. The heat spreads to adjacent cells, which overheat and spread heat to their neighbors.